Today we're going to be talking about section 8.1 about sequences and summation notation. This chapter is going to go really quickly, and you'll see today we're going to talk about a lot of definitions and notation that will help us understand what we should be doing and how we should be doing things with our sequences. Today we're going to talk about what a sequence is and what summation notation looks like and what its parts are. We're going to evaluate what we call a general term for a sequence, and that will allow us to find the value of specific terms in the sequence. We'll talk about what factorial notation means and then use that in sequences, and then finally we will find sums of sequences using summation notation, and then in fact write backwards summation notation. So a sequence is anything that has a pattern. Sometimes that pattern is recognizable, sometimes it is not. You've been working with patterns ever since you were in preschool or kindergarten. When you learned to count by twos, 2, 4, 6, 8, you were learning about a sequence. When you learned about colors and you put blocks out in a specific pattern, that was a sequence. All sequences can be infinite, which we know means it doesn't ever end. And its domain, things that are part of it, are all positive integers. We use a sub n as the notation to describe any infinite sequence. That n that is here represents what we call the nth term. Now that nth term is a term that is unknown at this point. We don't know its specifics. When we change that n to a specific number, and we call this a sub 20, now we're saying that we're talking about the 20th term in a given sequence. Okay? Anytime a sub n equals like an expression, 2n minus 7, this expression right here is what we call the general term. Let me spell that correctly. General. That's why I do math and not English. The general term expression. A general term expression is an expression that describes how we find the value of a term in a specific sequence. So this 2n minus 7 describes a very specific sequence. Now we can use it to find any term. So if I want to find the first term, then I'm finding a sub 1. If this n changes to a 1, then this n would change to a 1. So if I'm given the general term, then I'm able to find the value of any term I want in this specific sequence. That's what we're going to do first, right? The first 4 terms of each sequence where the general term is given. So this general term right here is describing a very specific sequence. If we want the first 4 terms, we want a sub 1, a sub 2, a sub 3, and a sub 4. Okay? That is meaning I'm finding that's the value of the first term, or I'm finding the value of the second term. So you'll notice that because my n here changed to number 1, then this n here changed to a number 1. Same thing with 2, or the second term, and the third term, and the fourth term. So once I replace n with the number of term I'm trying to find the value of, I can evaluate this using the order of operations to get my term. So the first term is 2 times 1 plus 5, which is 7. 2 times 2 is 4. 4 plus 5 is 9. So my second term in this sequence has a value of 9. My third term is 6 plus 5, which is 11. And 8 plus 5 is 13. So this specific sequence has a first term of 7, second term of 9, so on and so forth. I could use this general term to find the value of the 50th term if I wanted. 2 times 50 plus 5. We know 2 times 50 is 100. 100 plus 5 means my 50th term would have a value of 105. I can use a general term for anything. Okay. Here's another one. We still want the first 4 terms. I'm going to write it over here so I have more room. We're just showing you this one to show you that sometimes our pattern isn't always recognizable. Again, if I want the first 4 terms, I want a sub 1, a sub 2, a sub 3, and a sub 4. So the first term, my n's changed to a 1. Negative 1 to the first is negative 1. 2 to the first is 2. 2 plus 1 is 3. My first term is negative 1/3. My second term, n's changed to a 2. So negative 1 squared is positive 1. 2 squared is 4. 4 plus 1 is 5. My second term is 1/5. Third term, my ends change to a 3. Negative 1 cubed is negative 1. 2 cubed is 8. Remember, 2 times 2 times 2, not 2 times 3. 8 plus 1 is 9. So my third term is negative 1/9. And my fourth term, my ends in the general term change to a 4. Negative 1 to the fourth power is positive 1. 2 to the fourth is 16. 16 plus 1 is 17. So this pattern isn't as recognizable, if it's recognizable at all. I changed from negative to positive, from 1 to 2 to 3 to 4, and then my denominators changed. So this one is not a very recognizable pattern, but because it has a general term expression of negative 1 to the n power divided by 2 to the n power plus 1, it is still considered a sequence. Okay. Factorial notation is when we are trying to find a product of something from one number through its positive integers down to 1. So we use this exclamation point to describe that we want to find a product of this nature. So for example, 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. If you plug all of those products into your calculator, you will find out that the value of 6 factorial is 720. You can find this feature on your graphing calculators under the math key. If you want to type in 6, hit the math key. You then have to scroll over using your arrow button to the PRB tab up at the top. That is probability. And you would see the exclamation point under the fourth option. Okay. In your scientific regular calculators, you do have a PRB option. You'll just have to hit PRB and then use your arrow to scroll over, and you should be able to find it there. Factorial notation does have some rules. The first one is that the value of 0 factorial is equal to 1. It's kind of similar to 0 as an exponent. Any base to a 0 exponent is 1. Same thing here. Anytime you're working with a quantity of 0 that is being factorial, that quantity would be 1. Then remember that that quantity could also be multiplied by something else. Like this here, this means 3 times the sum n plus 1 factorial. So if I'm trying to find the fifth term here, and this is my general term, it would be 3 times 5 plus 1 factorial, which means 3 is going to multiply by the value of 6 factorial. We already know 6 factorial from up here is 720, so 3 times 720 is going to give me, I don't have my calculator out, so I'm going to do this by hand, 2,160. You have to make sure you're applying that factorial to only the part of the expression that it says to be applied for. This says 3 times this sum's factorial, so we have to find the sum, as our order of operations tell us, and then factorial it. Okay. If you're looking at your lecture note guide here, you don't have this 2 here. Please make sure you put it there so you can follow your example when you're working on your homework. Again, we want the first 4 terms. So 20 is going to divide by 2 times 1 plus 1 factorial, which means 20 is going to divide by the product of 2 times 2 factorial. 2 factorial means 2 times 1. Okay, so 2 times 1 means 2. So 20 will divide by 4, which gives us an a sub 1 value of 5. Do that same thing with the next term. 20 will be divided by 2 times 2 plus 1 factorial. That means 20 is divided by 2 times 3 factorial. Okay, so 3 factorial means 3 times 2 times 1, which is 6. So 20 is going to divide by 12. We know that that does not reduce into a whole number, but it is a reducible fraction. it will reduce by dividing by 4. So we get 5 on the top, divide by 4 on the bottom, and we get 5/3 as a second term. Two more terms here. 20 is going to divide by 2 times 3 plus 1 factorial. So 20 will divide by 2 times 4 factorial. So 4 factorial means 4 times 3 times 2 times 1, which is 24. So 20 will divide by 48. And again, we can reduce that by dividing by 4. 20 divided by 4 is 5. 48 divided by 4 is 12. So we have a third term of 5/12. Last term here, 20 divided by 2 times 4 plus 1 factorial. So 20 is going to divide by the product of 2 times 5 factorial. 5 factorial means 5 times 4 times 3 times 2 times 1. That value is 120. So my denominator, when I multiply 2 times 120, is 240. And that can reduce by dividing by 20. And we're going to get 1/12. Notice that I'm showing my work for all of these. It is very hard for me as your teacher to grade your work with a wrong answer. If I don't have work, I don't know where that mistake is happening. Pay attention to the order of operations. Read this out loud so you make sure you're doing it in the correct order. Next thing we're going to talk about is summation notation. Summation notation is just a fancy way of telling me to find the sum of something without having to write it all out in a sentence. This is summation notation. This fancy looking E right here is the Greek letter for sigma. Mathematically, sigma always stands for the sum of something. So when you see this symbol, it means find the sum. Sum means to add. Okay. Now what are we finding the sum of? These other 4 parts tell us what we're finding the sum of. This right here is going to be an expression that represents your general term. Remember, that is the expression that tells us how to find the value of terms in that given sequence. We're used to that being a sub n. Here they're traditionally going to use an I. Okay, that I just is going to match this I. This variable right here is called the index. Whatever that variable is going to be the same variable that's in your general term expression. If you look down here, there's a k as my index, there's a k in my general term expression. Those are always going to match. The number that that index is equal to is what we call the lower limit. That lower limit describes the term the sum starts with, because it's not always going to start with 1. Okay, it can start with anything. So if I is equal to 7, then that means the 7th term is the first term of my sum, or I'm starting that sum with the 7th term. Up here is going to be a number that represents our upper limit. Well, if the lower limit is the term the sum starts with, the upper limit is the term the sum ends with. Okay, so here's a summation notation. What does this mean? We always start with the sigma. Sigma means find the sum. What are we finding the sum of? We're finding the sum of the sequence, in this case. That sequence is called 2k. So find the sum of the sequence 2k from the first term through the 16th term. So that would mean we would have to use the general term expression of 2k to find the value of the first term, and find the value of the second term, and find the value of the third term. And we would have to find the value of all 16 terms so that we can add them up to get a sum. So find the sum of the sequence 2i squared from the first term through the sixth term. That means I need term 1, term 2, all the way through term 6, so that I can then add them up to find the sum that they are asking for. Now, if you have to have the value of 6 terms to get the correct sum, then that means these are very crucial. You have to make sure those are correct. So the first term, we know if our general term is 2i equals 2i squared. If this I changes to a number, then this I changes to a number. So we're going to find the first term and the second term, which means my i's are all changing to the numbers that I need them, or the term that I need them to be. And then follow your order of operations. We have multiplication and an exponent. Exponents come first. So 1 squared is 1, 1 times 2 is 2. 2 squared is 4, 4 times 2 is 8. 3 squared is 9, 9 times 2 is 18. 4 squared is 16, 16 times 2 is 32. 5 squared is 25, 25 times 2 is 50. And 6 squared is 36, 36 times 2 is 72. These are my 6 terms, but they're asking for the sum, so my answer is what all of those are added up, which if you're adding them right now, you should get 182. If you do not show me your work for those 6 terms and your sum is wrong, I have to count all of them wrong, so please make sure you show your work. Here's another example. Here, my lower limit is 3, my upper limit is 5, so I want terms 3 plus 4 plus 5. So my general expression is 2k, 2 to the k power minus 3. So I'm going to find 2 to the third power minus 3. Add that to 2 to the fourth power minus 3. Add that to 2 to the fifth power minus 3. 2 cubed is 8. 8 minus 3 is 5. 2 to the fourth power is 16. 16 minus 3 is 13. 2 to the fifth power is 32. 32 minus 3 is 29. Third, fourth, and fifth, the sum of those is 47. Last example here in this, remember that if our index is I, then that means A sub I equals our general term of 4. This general term is different than any of the others because it doesn't have a variable. That means we can't manipulate what this value is. If A sub I equals 4, if I want my first term through my fifth term, then if I is changing to a 1, then this is still 4. I is changing a 2, this is still 4. When your general term is just a number, that means each term has that exact value. So we add all of those up, and we get a sum of 20. Now the last thing we're going to do is use that summation notation backwards. Express each of these sums. So they're not telling us what the sum is, but they're showing us how we would get a sum. And we want to express those in what it would look like in summation notation. They're telling us to use 1 as our lower limit. That means this is going to be a 1, and I for our index. That means once we determine our general term, the variable we're going to use is I. If 1 is our lower limit, then that is describing that this is the first term, which then means this has to be the second, this has to be the third, and so on and so forth. So remember that in any general term expression, I'm just going to use this one because we've already done it, when n changes to a 1 or our variable changes to a 1, then our general term, wherever there was a variable, it had to change to a 1. So if my first term is found by taking 1 and squaring it, my second term is found by taking 2 and squaring it, my third term is found by taking 3 and squaring it, that means my general term had to be an I that I squared, because this I changed to a 1 to get my first term. This I changed to a 2 to get my second term. This I changed to a 3 to get my third term. Which then means this has to be my ninth term if I change to a 9, which means my upper limit is 9. We're going to do the same thing for these others. I is my index, lower limit is 1. That means this is my first term, this is my second term, and this is my third term. I hope we can all agree that my general term expression has to be a fraction, since these are all fractions. And if we notice that my first term has a numerator of 1, my second term has a numerator of 2, and my third term has a numerator of 3, that means my general term had a numerator of I, because that I changed to a 1 to match the first term. I changed to a 2 to match my second term, and so on and so forth. Since the numerator of this one is a 16, that has to be the 16th term. So my upper limit is 16. The only thing that's left to determine is this denominator. Now these don't help us. They don't match the number of terms that we're dealing with, and they don't tell us how they got 3, 4, and 5. But this does tell us something. If this is the 16th term, then remember a variable had to change to 16. So this 16 was originally an I, which means all of these expressions are found by taking I divided by I plus 2. This last one, I'm going to make that a fraction. We know that this is term 1, term 2, term 3, and term 4, because they tell us that our lower limit is 1. If all of our numerators are a 1, then that means there is a 1 in our general term expression. It doesn't change. Now this last term is a little bit different than the others because it doesn't have any other numbers in it, but it does have this n. Remember, n stands for the nth term. That means this term, we don't know what specific term it is. This, because there's an n there, is representing the nth term. So that means this n replaced the I in my general term. If your nth or your last term is an nth term, this expression is representing your general term, but your n has to change back to an I simply because they're telling us our I is an index. That is it for section 8.1. Please make sure you complete section 8.1 My Math Lab assignment for the next class. If you have any questions, please email me, and I will see you soon.